Welcome. This is Dr. Morton, and I'm going to cover Chapter 16 of Logic Design this evening. This chapter is on the hardware description language, Verilog's way of implementing sequential logic. Obviously, within this logic design course, the introduction of hardware description language is just to give you a bit of a feel. It's just an introduction. So we've covered combinational design. We've covered some of the rules, how you do combinational statements, and we've even talked about how you can use always blocks to which are intended for sequential logic, but how you can use those to make combinational logic. Now we're going to actually talk about how we could use them to make what they're really intended for, sequential logic. So let's go through that. Okay, so let me transition here to the book, and so here is sort of the I don't know the icon, I guess, for this chapter, and what you can see here is sequential design in Verilog, and you can see Verilog code here, D flip-flop, shift register, state machines, a whole bunch of stuff. So that's what we're going to cover. Here are the learning objectives. Let me put these on the. Let me transition these to the slides, so I think it's a little bit better example. So I want you to be able to design a D flip-flop with using Verilog, using the Verilog hardware description language. I want you to be able to describe how the always block sensitivity list controls execution of an always block, and I want you to be able to design a D flip-flop with an asynchronous clear and set inputs in Verilog. So that's what we're going to attempt to cover here. Okay, so let me go on down. Maybe I'll go back to the book. Let's see. Let me just transition back and. Okay. So here's our book. Same learning objectives. I just covered them. A few terms in the glossary. Always block, pos edge, and neg edge signals. So we use these designations of pos edge and neg edge to apply to our edge signals in our sensitivity list. And I'll explain that in a minute. And then I also introduced terms like soft core and hardcore, and they refer to when we actually make a microprocessor, when we create one on an FPGA, and if we create it with after the FPGA is made, we call it a soft core. If it's coded in as the FPGA is made, then we call it a hardcore. All right, so if you have any question, you should probably go back to Chapter 9 and review the Verilog basics so you kind of get back up to speed. We haven't talked a lot about Verilog since then. And you should also look at how we compared the function of creating a multiplex on an FPGA, a multiplexer on an FPGA, say in this case a 41 mux, versus implementing one with a microprocessor. And you could see just quite a difference because just of the fundamental differences in programmable logic and microprocessors. Again, microprocessors are hardware that's already been created, manufactured in the form of an integrated circuit, and they execute a program that's stored in their program memory. An FPGA it's an integrated circuit that's also already been made, but in its native form, it doesn't do anything at all. You have to create a bit file using an integrated development environment and a fairly complicated synthesizer to take your hardware description language description of the circuit you want to create and turn that into a bit file that when you write into the FPGA turns it into that type of hardware. Okay, so go back and look at Chapter 9. I think that'll help you understand a little bit better what's going on in this chapter. All right, so remember, we talk about combinational circuits and sequential circuits. Remember, the distinction between them is in a combinational circuit, you have some inputs, a network, and some outputs, and the current inputs fully determine what's going to happen with the outputs. You don't have any memory of any prior history in a combinational device. In a sequential device, you basically have a state machine, and you encode some history of prior inputs in the form of states. And the more states, the more complicated that history can be. The fewer states, the less complicated it can be. All right. So, when we create a register, which we didn't really do in our prior description, when we create this register, we can write something like reg, and then bracket 3 to 0, close bracket, variable a, and then a closing semicolon. What actually happens here is we've created 4 flip-flops to hold the 4 bits that we've called variable a. So just this statement by itself actually creates flip-flops. The synthesizer looks at this statement and says, okay, you need a register with 4 flip-flops. And that's what it does. It makes 4 flip-flops. Now, because it actually will do that, normally we don't create modules that define a flip-flop unless we're making some kind of very unusual type of flip-flop or something. But because a flip-flop is such a common thing and fairly well understood, it's the perfect example of a sequential device that we use as an example of how we can do this with a hardware description language like Verilog. So we're going to use the Verilog description of a flip-flop as our example of a sequential design, even though we would rarely do this in practice because all we have to do is write this simple statement to actually get 4 flip-flops and a register made. All right, so it's kind of it's really for academic reasons we're doing this. Okay, so if we scroll down here is a module. That's the Verilog code to make a D flip-flop. All right, now I'm going to go back to the slides for a second. So 1 second here, and we'll flip over. So again, so remember, we're just going to do an introduction. We're not going to do an exhausting treatment of how to make sequential devices with Verilog. Okay, so in logic design, and of course in Verilog, there are 2 types of codes. There's continual assignments, and there are procedural assignments. All right, so continual assignments are like combinational devices. You have some signals on the right-hand side, and they give you a result that's the left-hand side. The outputs depend only on the current inputs. There's no memory and typically no clock. A procedural assignment, on the other hand, this is basically how we make state machines. And that's what we've been doing in this second part of the course. The outputs typically depend on some history of prior inputs. They typically do have clocks, or a clock, or more than one clock. And they typically use flip-flops to help us remember what state we're in. Okay, so within Verilog, we have what are called 2 procedural blocks. One is called the always block, and the other is called the initial block. And the keywords for the always block is always, and the keyword for the initial block is initial. Now, the initial block is executed on startup, and once it finishes, it is not executed again. Now, it depends on what your target hardware is. If your target hardware is an integrated circuit, then the initial block is not synthesized. It is just used in your test bench to test your design. But if you're making an FPGA bit file, then the initial block can result in the startup values of a number of your variables. And so it is synthesizable in that regard. So again, depends on your target hardware. A brand new integrated circuit, not synthesizable, just for simulation. But if you're using an FPGA or some other programmable logic, then you can use an initial block in most cases to initialize the various variables in your design. All right, the always block on the other hand, so that's the initial block. The other procedural block is the always block, and it is executed whenever the signals in the sensitivity list change. And if they're designated edges, then they're executed when it has the designated edge, pos edge or neg edge. All right, here is that same flip-flop we just looked at in the text. So this is a D flip-flop. Now, this is the whole entire module for this D flip-flop. So this could be a standalone flip-flop. If that was all the project had was one flip-flop, then this could be the whole project. But obviously that wouldn't usually be the case. Normally this would be a sub-module, and we would instantiate however many copies of this we needed in, say, higher level modules to create registers. Now again, we normally don't have to do that because we can just issue that one register statement, which we showed earlier. But we're doing it in this setting to show you how an always block works, and it's a great example for that. Even though you probably would never use this, you would make other things with always blocks, but you wouldn't make flip flops because they're easier to be made just by writing the statement reg 3-to-1 variable a, and now you've created a variable a with 4 flip-flops holding the 4 bits of variable a, or whatever. Okay, so with that understanding, here we go. So this module starts with a keyword module, as do all modules, and it ends with the keyword end module. And the guts of the module then are made up of its port list here, and then here we define the port list with a little more detail. And then we have an always block here. And then after the always block, we have one continuous assignment. This assign qn equals not q. And then we have end module, and that's it. Okay, so let's look at the always block. So, let's look at the port list first. So we list all the signals in the port list, but now we go through and we describe them a little more. So our signals are Q, Q naught, D, clock, and clear. So this is a D flip-flop with outputs Q and Q naught, and a clock, and an asynchronous input called clear. Now, our clock could be rising edge or falling edge. Our clear could be active low when it's asserted, or it could be active high when it's asserted. So here we're going to describe these signals a little better. Wire. So we're saying that D is a wire and it's an input. Clock is a wire and it's an input. And clear is a wire and it's also an input. Okay? And then we're saying that Q is a register and it's an output. And Q naught is a wire and it's also an output. So now we've described these signals in a little more detail. We know which ones are inputs, which ones are outputs, which one is a register, and the rest are all wires. Now remember, a register is basically a flip-flop. So that's kind of funny, right? But that's what we're making here. All right, so then we get to there are no internal variables. All the variables in this module appear in our port list. So now we have an always block, and so that's the keyword always, and then we use an @ sign. Now in this case, we have parentheses here, and we put what's in between our parentheses is our sensitivity list, and we write in here pos edge clock, comma, pos edge clear. Because these are edge signals, that's the first clue that this is for real combinational sequential device, not a combinational device. Back in chapter 9, when we showed how to use always blocks for combinational devices, we never used edge signals. We didn't put clocks in here. We only used level signals, and sometimes we use a special designation called we didn't even have the parentheses. We just had an asterisk here, and that meant include every signal inside the always block in its port list, in its sensitivity list. We call this a port list. We call this the sensitivity list. All right. Now we also use keywords. So let me show this. So first off, we have the keyword always here, and the always cannot be by itself. It must be inside a module. Okay. Secondly, we have the sensitivity list, and if we intend this always block to be a state machine, a sequential logic, then we normally have edge signals in this sensitivity list. In Vivado, the program we use in digital systems design for our FPGAs, it only allows you have to either have all level signals with no edge designations, or you have to have all edge signals with either pos edge or neg edge designations. In this case, both clock and clear are pos edge designated. There should be a space here. All right, then our always block begins with a begin statement and ends with an end statement. And within that are the guts of the always block. So what are the guts? Well, we have an if statement. Remember, you can only use if statements in always blocks. You can also only use for statements, while statements, do while statements, and case statements in always blocks as well. They cannot be used outside of always blocks. Must be inside an always block. All right. And what it says inside here is, if clear equals 1, then set Q. And remember, we talked about how constants are used. I think, honest to goodness, I think that's an O and not a 0. I'll fix that in a minute. Okay, so we have if clear equals 1, set Q to 0. All right, and remember how we did the constants. 1 tick, our base binary, and then our digit 0 in this case. All right, and then if this isn't true, else Q equals D. So if our clear is not asserted, and remember, since it's a pos edge, it's an active high clear. If the clear is equal to 0, which means it's de-asserted, then we set Q equal to whatever the value of D is. And D comes in our port list up here. And that's the end of the if statement. And that's also the, well, let's see. Our if statement didn't have begin and end. If we had more than one line, we would have to have used begin and end in this as well. Basically, in Verilog, we substitute begin and end for the curly brackets. That's kind of the best way to think of it. We do not use curly brackets in Verilog except for the concatenation operator. All right, and then finally, outside of this always block, now we're done with our always block, we have this a continuous assignment where we use the keyword assigned. We saw this keyword used in chapter 9. And what we do here, we set Q naught equal to the inverse of Q. Now we could have defined Q naught also as a register, like we did Q, but we actually defined it as a wire instead. And then here we assigned Q naught, we assigned not Q equal to Q naught. Remember, Q and Q naught should always be the opposite. Those are the outputs from our flip-flop. In our port list, outputs can be registers or wires, but inputs must be wires, and if we have bidirectional signals, they also have to be wires. All right. Notice inside the always block, our signals on the left of the equal sign, or the operator. Well, in this case, we have two different equal signs we can use in always blocks. Assignment operator here, and that's the non-blocking, and that's the blocking. And I mixed them, I guess, just for grins. Normally, in an always block that's intended to be sequential logic or a state machine, we would use the less than equal construct, which is the non-blocking operator. And normally, if we're doing it for combinational logic purposes, we would use these blocking operators. We sometimes will use these, though, as I did here, in an always block that is really resulting in sequential logic. Notice, though, that the signal, the Q here, must be defined as a register. Now, we had this same requirement back in Chapter 9 when we used the always block for this, for combinational logic. In other words, always blocks were basically created to make sequential logic, but this bastardized use to allow them to be used for making combinational logic is permitted, but there are some constraints, and one of those constraints is when we use them for combinational logic, we have to define these signals on the left as registers, but the synthesizer knows that we don't intend this always block to be sequential logic, and so if you don't make a mistake, it will convert it all to combinational logic, and the signals which you defined as registers will not actually be made as registers. Otherwise, that would mess up using it for that bastardized purpose. Okay, but here we're using it for the intended purpose. Again, this is actually going to result in a sequential device, a flip-flop. All right. And then finally, down here, we have our end module statement. Well, there's our continuous assignment. And again, the continuous assignments can't be inside always blocks. They have to be outside always blocks. And the left-hand side, that continual assignment statement, this Q naught, has to be a wire, which we covered in Chapter 9. Okay, now, remember, after the module keyword, we put the module name, and this D_FF for D flip-flop. We have our port list, and then we define the signals a little better. You can put that all in one list if you want. That's another way to do it, but this is the method I suggest you use. Then, if we had any internal signals, we'd define those after this, but there aren't any internal signals in this module. All the signals used in the module do appear in the port list, but that's not a requirement. You can have lots of signals inside the module that never leave the module, that are just used internally, but we just don't happen to have any in this case. We use the always keyword and the sensitivity list, as we talked about. And then we have the body of the always block, and this between the begin and end statements. And that body of the always block was just an if statement here, an if and an if else, or an if and then an else. And then after the always block, we have this one continuous assignment statement. And then end module. And that's it. Okay, so when you want to use an always block for not for sequential logic, but for combinational logic, here's what you have to keep in mind. So Verilog will allow the use of an always block to make combinational logic, even though it's not the intended purpose. But the synthesizer is smart enough to figure out that it should be combinational logic. This allows the designer to use the always block for convenience. So he can use she can use things like while statements, case statements, if statements, for statements. They're only legal in always blocks. So if you want to use those, but you want to use them on combinational logic, then you have to then you can use an always block, but you have to be careful that you don't accidentally turn it into a sequential result. So it allows these statements to be used for combinational logic. We typically only use level signals in the sensitivity list and no clocks. So there's no edge signals and there's no clocks. If every possible condition is not accounted for in the always block, then it may make a latch. And that means it won't be combinational logic, it will be sequential logic, which you didn't intend if you're using it for this bastardized purpose. And finally, we have this special syntax, always asterisk. So we don't actually have a sensitivity list. This asterisk means all the signals that show up in the block are automatically included in the sensitivity list as level signals, not as edge signals. Okay? Okay. So let's go on here. So here's a JK flip-flop, just a little more complicated. And you can see we did use the concatenation operator inside here. We concatenated J and K, each 1 bit, to give us a 2-bit variable. And this 2-bit variable then is spelled out in our case statement. If they're both 0, then we hold. If J is 0 and K is 1, then we clear the flip-flop. if they're both, oh, this is a mistake. Okay, hang on. Okay, with the slide fixed, so if j and k are both 0, we hold. If j is 1 and k is 0, we clear the flip-flop. If j is 1 and k is 0, I don't know. Well, anyway, if j is 0 and k is 1, we clear the flip-flop. If j is 1 and k is 0, as in here, we set the flip-flop. And if they're both 1, we toggle it. We set q equal to the bitwise inverse of q. You could also use the logical. Whenever you're dealing with a single bit, the logical and bitwise are the same. So that's okay. All right. And then, end case. Notice in C, in a case statement, we have to have a break after every one of these, or it'll just continue to execute through them all. But in the case of Verilog, the break statements are not required. It's a little bit different. The case statement's just a little bit different than how it is set up in C. Okay, and then we have end for the always block. And then we have an assignment again outside of the always block. Now this assignment has to be a combinational assignment. So this assigns the wire, the left-hand side here, Qn has to be a wire, and that's how it's defined. And we set it equal to the inverse of the register Q. Okay, and that's all there is to it. This makes a flip-flop. In this case, a JK flip-flop. Here we have another example. Now, in this example, which I'll go through here in just a second, we're going to show you a register, and this register has 4 bits, which means 4 flip-flops. And we're going to make this the hard way. We could do it the easy way by just defining the variable as a 4-bit register. But instead, we're going to instantiate 4 flip-flops. Now, we might actually have to do this if our flip-flops were some kind of specialized flip-flop. But if it's just regular old D flip-flops, then Verilog will do all this work for you. You don't have to actually create a module for the D flip-flop and instantiate it. It's already built in. But I'm doing it here to show you an example of how a sequential design can be put together. So that's the idea. Okay, so let's transition, and I'm going to see if I can move this just a little bit. All right, let me fix that. Okay, now you can see the whole thing. And I should have probably made the font just a little bigger. Maybe I'll do that too. Okay, it's a little bigger now, and hopefully it's a little more readable. All right, so what do we have here? Well, module, the keyword module. Now we have the name, register underscore 4-bit. We have the port list, load, in, out, clear, and clock. All right, so load's an input, clear's an input, clock's an input, and they're single bits. The in is an input, and it's 4 bits, so it's a vector. It's not just a single bit. And then out is an output, and it's 4 bits. And then that's it. That's our entire port list. Now, notice we also have wire 3 to 0 dummy. So dummy is a 4-bit vector, and we're going to use that because we need, because we don't, when we instantiate our flip-flop, remember it has a Q and a Q naught, but we don't really need the Q naught in this case. So we're going to just let that be a dummy assignment. And we don't have to specify an input-output because it doesn't show up in the port list. And then we have wire D in, and we're going to do that just because of the way we're going to assign these things. So notice I don't have an always block directly in this module, but where I've instantiated 4 flip-flops, the flip-flop modules do have an always block. So I'm going to use this D in as the left-hand side of this assignment statement. Okay, and then the way that's going to work is that's going to be the input to our flip-flop. All right, so let's see if this makes any sense. So basically, what we have here is a 4-bit register that we can load a value in. What do we load in? We load in this variable called in. And then it can also just output what the current value of the flip-flop is, and that's just out. Okay? And then we can clear the flip-flops, and obviously on the clock edge we will latch in if we have if our load is in this case it's active high. If our load is high, we are going to load in whatever the 4-bit vector in has, and but it's not going to happen. It's not going to happen when it's not going to get loaded into the flip-flops when load changes to a 1 and is asserted, or when in changes. It's only going to happen on the clock edge, because here's where our flip-flops are actually instantiated. Okay, so let's do this. So a couple of things. So it shows how the D flip-flop we just created could be instantiated, that is, used in another module. Okay? And then it also shows how we might need to use a dummy variable when we don't need to use all the variables in the port list of this module we're instantiating. So in this particular case, notice, well, let's go back to our flip-flop. Here's our D flip-flop. So notice we have, in this port list, we have Q, Q naught, D, clock, and clear. Okay. So here's our register. Notice we have 4 instantiations. So we use the module name that we're instantiating, D flip-flop. We have to have a unique instance name. In this case, number 1, number 2, number 3, number 4. So we instantiate it 4 times. Each one has a unique name. And then we have our port list. And the port list must match the original module. So our D flip-flop module, this port list, the order of these variables must match. Now there's another way to do it called named association we're not going to cover. But if we don't use named association, then we have to use the exact order. So again, if we back up, the order was Q, Q naught, D, clock, and clear. Okay. So here it is, Q, Q naught, D, clock, and clear. But notice I don't put the names that were used in the module definition. I put the actual names here of the variables I want to pass to that flip-flop. So this is my first flip-flop, so I'm going to send out 0 as the output's going to be out 0. The dummy output would be the Q naught, but I'm not using that, so I'm just going to make that a dummy. And then my D in, if I'm going to latch the D in, then I would use D in 0 for this flip-flop. I would use D in 1 for this flip-flop, D in 2 for this flip-flop, and D in 3 for this flip-flop. That's my D in. And then here's my clock. And then if I'm going to clear the flip-flop, then that's my clear signal. Okay, so the clear signal is a single bit. The clock's a single bit. The D in 0 is a single bit. The dummy 0 is a single bit. And the output 0 is a single bit. But taken together, this gives me 4 bits of output and 4 bits of input. Same clock, same clear, and I used different dummies just because I would get an error if I tried to assign the same dummy simultaneously from 4 different modules. That would be a bit of a problem because there could be a short circuit involved in that. Okay, so how does this actually work? Well, what happens is this line right here this line, assign D in equals load, comma, in, colon, out. This assignment statement is a little tricky. So first off, notice that D in, load, and that D in and out are all 4-bit vectors, but load is a single bit. The way this works, I test load. If load is true, I assign in to D in. If load is false, I assign out to D in. So basically what happens is that my input, unless I get something else in here, well, my input that comes in from my external from my module port list will be here, and it's going to go to the D inputs if load is false. No, I said that wrong. It's going to go to the D inputs if load is true. So in other words, this input is what gets loaded when my load control signal is asserted. So if load is 1, then the input will be assigned to D in, and then my D in 0 will get assigned to the D flip-flop on the clock. The D in 1 will get assigned to the number 2 flip-flop on the D flip-flop on the clock. Then D in 2 will be assigned to number 3, and D in 3 to number 4, all on the clock. If, on the other hand, load is 0, then my output is going to be assigned to D in. Now, what does that mean? Well, what that means is then on the clock edge, I'm just going to connect the output, the current output of the flip-flop to the input. So in other words, my flip-flop will hold its value. And then so the clock can tick and tick and tick, but as long as load is deasserted, then the output's just going to be driven by the current input, and it's just going to hold its value. But if load is a 1, then I'm going to take whatever comes in on the 4 bits of in, and I'm going to put that into the D's, and that's going to be stored in the register. Now, if I want to clear the register to zeros, then all I have to do is assert clear, which would be high. So if clear is high, it will override the D in and the clock. All right, so that's how the register works. So I hope that explanation was somewhat useful. It's a little bit of a contrived example, again, because normally we wouldn't really write the Verilog code that way because the synthesizer will make the flip-flops for us. We don't have to use a flip-flop module. But that just shows you how we can create a sequential module and instantiate copies of it to get a sequential design. In this case, a 4-bit register that we can clear by asserting clear. We can load by applying 4 bits of D in and asserting load, or we can just let it hold its current value until we want to load something else. Okay, so this is a bit of a summary. If we have inputs, they have to be wires, and if we have bidirectional inputs called in-outs, they have to be wires. But if we have outputs, they can be either a wire or a register in our module port list. Okay? So that pretty much covers everything I wanted to go through. And hopefully this gives you some good insight. Let's see. I may just, let's do this real quick. So, yeah, we'll take this down. And we'll transition. Okay, sorry, it took a minute. All right, so I just want to go back through this, make sure I didn't miss anything here. So again, we almost every textbook I've ever seen, when they want to give you an example of a sequential design using an always block, they use a flip-flop, even though in practice we don't usually do that because these flip-flops are built in. Okay, and we kind of went over that. We talked about some of the rules for instantiating a module. So you have to give it a unique name, number 1, number 2, number 3, number 4. And the reason for that is that we can use these unique names, which every module is required to have, except for your top level module, I guess. And that basically allows us to dig down and get to any submodule, any submodule within a big project. And we do have some statements in Verilog that allow us to reach in and touch stuff in a module way down. But it's beyond the scope of this introductory course. Yeah, and I think we've covered all this. Yeah, I think we did all that. In the text, I also tried to compare sort of a register versus flip-flops in C++. And since flip-flops are a hardware item, so when we use a microprocessor, we don't normally create that. So it's a little bit of it's a poor example, but the way we would sort of do this with the microprocessor is we would just define, say, variables x and y, and they might be for any particular processor type and integrated development environment supporting that processor. They might be defined as 16-bit variables or whatever, and so this would actually allow us to store 16 different bits in x, 16 different bits in y. So this was just an example. So you can read through this and talk and see how that would be, how we would maybe implement that in a microprocessor. Okay, so I think that basically this chapter combined with chapter 9 gives you basically an overview of Verilog. Again, just an introduction. There's many more details of Verilog that we have not covered. Verilog in and of itself is actually a very complicated language to learn, and you do have to pretty much write code and then implement it in an FPGA to see if it'll actually work, because you can write code that looks fine, but it violates physical limitations and actually doesn't work right. So it can be really it can be tricky, and you have to learn it by doing. All right, with that I'm going to quit, and we will pick back up in chapter 17.